Is it visible now?
Good afternoon, everyone. My name is Jinji, and today my presentation is about the recovery of low-concentration ethanol from wastewater produced in traditional Chinese medicine industries by evaporation. And this is the outline of my presentation. I will first introduce the background of my project, and then the methodology, followed by some preliminary results and discussion. And the final part is the conclusion and future work. First is the background of this project. Traditional Chinese medicine, TCM, is one of the national quintessence of our country. It is the material basis for medical development in China. TCM has also played an important role in the prevention and treatment of COVID-19 during the pandemic. Generally, most of the TCM recipes or formulas are produced by the alcohol precipitation method to achieve good purification level, improve the product quality, and ensure the clinical healing effect. As shown in this flowchart, the overall manufacturing process of TCM products includes multiple steps, and it is actually struggling to meet the requirements of environmental friendly and sustainable production. That is mainly due to the significant amount of wastewater produced in the process. Researchers have shown that when total TCM product output exceeds 1,000 tons, then every ton of final TCM product means 130 tons of wastewater will be generated at the same time. And the wastewater actually contains a significant amount of ethanol because ethanol is a general solvent, always a precipitant, used in the extraction of TCM. The large consumption of the fresh ethanol also results in the high cost of the process, especially if it's not reused. And because ethanol is highly flammable, the storage of ethanol is actually another potential safety risk. Therefore, the efficient recovery of ethanol is crucial for the development of modern TCM production. Currently, there are several separation techniques can be used to recycle ethanol from the TCM wastewater, including distillation, evaporation, membrane distillation, reverse osmosis, adsorption, and etc. Evaporation has been regarded as one suitable choice due to its non-toxic nature and simple mechanism. As shown in this figure, the PV process is just driven by the partial pressure difference and concentration difference. The desired component could pass through the membrane based on the selective dissolution and diffusion mechanism in the vaporizing process. And as mentioned before, and also we all know that distillation column is one of the most commonly used technology to recycle ethanol from, especially when ethanol concentration is significantly high. As shown in this flow diagram, normally in a TCM manufacturing factory plant, the wastewater discharged from the production line will be first treated by the distillation column, and when the concentration of the vaporized ethanol is greater than 92%, it will be then transferred into an ethanol storage tank for subsequent use. On the other hand, when the ethanol concentration at the bottom of the distillation column falls below 30%, it's just discharged directly. But actually in this case, we can feed the bottom solution to the evaporation system for further recycling treatment. So in this work, a bench-scale evaporation setup was applied and a specific membrane module was designed. So during the PV test, the TCM wastewater will be kept at certain temperature and then pumped through the membrane module and then go back to the reservoir. And inside the module, the mixture solution will be forced to travel all the way through this long and curvy channel and in constant contact with the membrane pressed on top. This curvy maze-like channel design is to maximize the contact area and contact time between the membrane and the feed solution. The vaporized ethanol will then permeate through the membrane under vacuum and condensate in the cold trap, and this buffer bottle is just to protect the vacuum pump. The whole experimental cycle will last for 6 hours, and the permit in the cold trap will be collected every 1.5 hours. The ethanol concentration in the feed, retentate, and the permit will be determined using gas chromatography. In our preliminary study, we have prepared some PV membranes by simply coating a layer of PDMS on the support material by casting and then followed by curing and solvent evaporation. The PDMS we used was Sealguard 184 and solvent was isooctane, so the supporting material was PAN ultrafiltration membranes. PDMS dope solutions with 2 different concentrations have been used to prepare the PV membranes. So we first studied the effect of PDMS concentration on the ethanol recovery efficiency of the prepared membranes. Because the project is still in the initial phase and is given limited time, so we just use ethanol water mixture solution instead of real TCM wastewater to carry out the experiment. The initial alcohol concentration in the feed solution was fixed at 157.86 gram per liter, and the table on the top summarized the experimental conditions of the PV test. The table at the bottom indicates the flux of the 2 membranes, and the figure shows the concentration change. It can be observed that the membrane made by 30% PDMS concentration have very obviously higher selectivity with a slightly lower flux. This is because the higher PDMS concentration made the membrane surface more hydrophobic. So in this case, even if some water molecules are also vaporized due to the high temperature, it is still hard for them to penetrate into the membrane and pass through, going to the permit side. So based on these results, we decided to use 30% PDMS membranes in all the following experiments. Apart from the PDMS concentration, we also investigated the effect of casting thickness on the ethanol recovery for different membranes. As shown in this table, if we compare the ethanol concentration change of the 20 micron thick and 14 micron thick membranes, it could be found that the membrane with larger thickness shows better ethanol selectivity, and this is probably due to the increased membrane resistance for water molecules to diffuse through the membrane, especially the coating layer. However, if we increase the membrane thickness further to 16 micron, then the membrane selectivity for ethanol disappeared, which was quite unexpected. And we guess this may be attributed to the significant high diffusion resistance due to the ultra-thick coating layer. So in this case, both ethanol and water molecules were impeded by the coating layer itself. Another possible reason is that our self-made membranes may have some defects or pinholes, which will also reduce the membrane selectivity. Further experiments will be conducted to explore the exact reasons behind this unusual phenomenon. Apart from the membrane itself, we also studied the effect of the experimental conditions on the ethanol recovery efficiency. But unfortunately, we only have time to run the PV test at 2 different temperatures, that is 60 and 70 degrees Celsius. And here we assume that the system is isothermal and the local temperature change can be ignored. The results in the scattered plot show that the membrane flux, generally the membrane flux is decreased a long time despite of the feed temperature, but obviously higher feed temperature leads to larger flux. And it's also noticed that increasing the feed temperature could increase the ethanol concentration in the permeate as well, as shown in this bar chart. And this could be attributed to two reasons. One is the mass transfer coefficient of the molecules, and the other is the absorption of molecules into the membrane. According to the literature, the effect of increasing temperature is positive on diffusion but negative on absorption. When the feed temperature goes higher, then the free volume in the membrane will increase, so the diffusion rate of the molecules through the membrane will also increase, resulting in a higher permeation flux. And also, the equilibrium vapor pressure of the molecules will also increase as temperature increase, which gives higher, larger driving force of the whole PV process. And also, this also contributes to the higher flux. So to sum up, basically, the evaporation system for ethanol recycle from the TCM wastewater has been found to be technically feasible, and we have conducted a series of experiments to develop a possible design for the PV test. It was found that the optimal design is to conduct the PV test at 70 degrees Celsius, use 40 micron thick membranes, and which are prepared from the 30% PDMS solution. However, there are still some limitations in this research that can be further improved. For example, our self-made membranes can recover some ethanol indeed, but the selectivity is poor. This can be further optimized by applying multi-stage evaporation. And we also plan to purchase different types of commercial PV membranes to evaluate their performance in our system as well. And furthermore, we will add some bioactive compounds of TCM into the feed in the future work to better mimic real TCM wastewater. And that's all for my presentation. Thank you for your time.
Thank you very much for the nice presentation. And since we needed to go to the closing ceremony quickly, so if there's a quick question, I can accept that, or otherwise, I will just have the conclusion on this session. Okay, I guess there's no question.
So we can join the closing ceremony. Thank you, everybody, and we can see you soon, very soon, in the closing ceremony.
Yeah, thank you very much.
Thank you. Please click the closing ceremony in the event schedule. See you.